Thank you very much for that generous and detailed introduction, Vice Chancellor, and for presiding over the proceedings today. It's a great honor. Can everybody hear me okay? Yes. There are a number of people that I'd like to thank on this occasion for helping me get this far in life. So I hope you won't mind if I just mention some people very briefly. I promise not to go on about anybody or start weeping in the manner of an Academy Award acceptance speech. To my parents and sister back in Korea, I'd like to record my deepest thanks and regrets for being so far away from them. The next person to thank is my wife, Gretchen Sigler, who is happily right here in the audience. And I'm gratified to have my brother and sister-in-law here. My brother, the economist Ha-Jun Chang, has been a Cambridge academic for a long time. He always thought it would be a good thing for me to join him, and he only had to wait 24 years. The one regret I have on this happy occasion is that he should be at my inaugural before I heard his, even though he deserves a chair much more than I do. But I won't say any more about that now, as that would be impolite. I would like to thank all my teachers and mentors. There are so many that I just picked my top 12. Hughes Pack, Glenn Vandervliet, Bruce Kane, Dan Kevles, Jim Woodward, Herb Bernstein, Jay Garfield, Nancy Cartwright, Peter Gallison, John Dupre, Gerald Holton, and Thomas Kuhn. And it's more than a baker's dozen, as I should add Jeremy Butterfield, Michael Redhead, and Simon Schaffer, who has kindly guided me ever since I was a visiting student here briefly in 1992. I'm grateful to all my colleagues in my department and the Whipple Library and Museum, at Clare Hall and elsewhere in Cambridge, especially John Forrester, Martin Harris, and Robert Anderson. Also to my longtime colleagues at UCL, which was my home for 16 years. UCL made me what I am, and that's not going to be forgotten. And it's great to see other colleagues from many far-flung places, so thank you all for being here. For organizing today's proceedings and facilitating what we are celebrating today and much else in our academic lives, I thank Tamara Hugg and the rest of the admin team in the department, and Debbie Patterson-Jones and Jane Vaughan Lane at the development office. And last but not least, students, past and present. I'm so pleased to see so many of you here today. I never wanted to become one of those professors who didn't enjoy professing. So you're ultimately the main point of this event. So welcome. Now let me say a few brief words, a personal word about the Hans Lausing chair that I've come to occupy. It is a pleasure and a relief to have benefactors whose values I appreciate and respect, especially their support for conservation, scholarship, and social justice, not to mention Lisbeth Rausing's considerable professional standing in the history of science. On behalf of all the people who benefit from their gift, I'd like to record our most sincere thanks to the Rausing family. I would also like to honor my predecessors, whom the Vice Chancellor has kindly mentioned. Professor Mary Hesse, who unfortunately couldn't be here. She wasn't feeling well today. I grew up reading her books as an undergraduate student, her pioneering works that changed the face of philosophy of science, and I still use them for my own teaching. I just did on Tuesday. I'm thrilled that she is still here with us, although she couldn't come to this event. And then Michael Redhead, who did so much to advance the philosophy of physics in Cambridge and elsewhere. In 1988, I applied to do a PhD in physics here in Cambridge. I never heard anything back from the physicist. But I got this nice letter from Michael. Can you read that? It says, your application to work on foundations of theoretical physics has been passed on to me. We have a group of 7 people, blah, blah. I would be very pleased for you to join us in the department. So that was nice. But I was also confused. Had I just got accepted into a graduate program that I never applied to? I couldn't take up the offer for lack of funding, and it was beyond my imagination then that Michael would one day be encouraging me to apply for his old chair. I'm so sorry he couldn't be here today. Michael, of course, was succeeded by the late Professor Peter Lipton, during whose tenure the chair came to be named after Hans Rausing. I regret so much that I didn't have a chance to get to know Peter well and to learn from him personally, though I did study his wonderful book and used it in my research and teaching. Peter had so many virtues, but one thing everybody will surely remember is his wonderful sense of humor. One of his jokes that still sticks to my mind goes like this. 4 American tourists came to Cambridge and agreed that they should see the famous King's College Chapel. So they came to King's College and they were told to just go through to the main court and they'll see it. But being a bit unfamiliar with things, they couldn't tell which bit of what they were looking at was the chapel. So one of them thought it was to their left, one said it was obviously what was on their right, and another one said it was directly in front of them, and they started arguing, and it all got very unpleasant. Finally, the 4th man spoke up and said, "Guys, let's not fight. Whichever one it is, we've seen it now." I've often thought that this gentle and witty American in the heart of Cambridge was the perfect image of Peter himself, who made peace through impeccable logic. Later this evening, we'll also be celebrating the lectureship now established in Peter's name, to which my colleague Helen Curry has been appointed. So it's doubly special to have the presence of the Lipton family, Diana, Jonah, and Jacob. And I'd also like to say a warm welcome to Professor Milikowski. Just one practical note before I begin the actual lecture. I had hoped to have a question period at the end, but due to serious time constraints, so as not to keep you from the reception and the drinks there, I've given up on the idea. But I'd like to ask you to feel free to contact me with any issues you want to discuss, either at the reception or later in person or by email. So there's my address again at the bottom. Let me begin with a direct question. What is the point of this strange academic discipline called the history and philosophy of science? Why should a respected institution like Cambridge University maintain a whole group of scholars and an established chair in it, and even house us in a grand historic building, even if it has to declare in big letters it's something else? What exactly does everyone gain from this considerable investment? Moreover, why should scholars in this field be kept in a separate enclosure, apart from other historians and other philosophers, and apart from the scientists? And why do we insist on putting the history of science and the philosophy of science together, constituting history and philosophy of science, a cumbersome name that we can only cope with by abbreviating it to HPS? I would like to propose some answers to these questions. My viewpoint is idiosyncratic and not necessarily shared even by my own colleagues. And I would not dream of suggesting that history or philosophy of science done from other perspectives is lacking in validity or value. But I do hope to convince you that my proposals deserve consideration. My main idea is that HPS, as a distinct academic discipline, is and should be an expression of pluralism concerning science. By pluralism here, I mean a commitment to maintain multiple systems of knowledge in each field of inquiry. Such pluralism is contrary to the dominant inclination in science as we know it. Modern science has developed largely in a monist spirit, looking for the one scientific truth about the one reality that we all inhabit, assuming there is one right answer to each scientific question and one best method for arriving at that right answer. I believe that a true appreciation of the significance of HPS as a serious academic endeavor implies a rejection of monism about science. Let's ask, why should any talented scholars want to devote their lives to HPS? To what may seem like a futile study of the long-abandoned past of science, or an idle questioning of the nature and foundations of scientific knowledge? Because such investigations are not truly futile or idle, no matter what mainstream scientists may tell us. Because it is possible and beneficial to consider alternative ways of knowing. Because it is important that we preserve our capacity to make independent judgment about the claims and the merits of science, rather than allowing ourselves to become blinded by the brilliant light of the astonishing successes of modern science. HPS practiced in this pluralist spirit opens our scientific minds, and that is good for science and good for all of us who rely on science. Pluralism about science is an unusual and controversial stance, so it requires a robust defense. You will find my attempt at that defense in the last chapter of my recently published book, but today I'll have to be more brief. One important lesson I learned from observing Peter Lipton was that every significant philosophical point can be expressed in a joke. So here's one for pluralism, which some of you have heard from me before. It's a brief dialogue at school. So the teacher tells a naughty student, "Your composition on my dog is exactly the same as your brother's. Did you copy his?" And the student replies, "No, sir, it's the same dog." Same dog. My mother-in-law sent me this one, not knowing what a profound impact it would have on my academic life. I wish one day we could have crowds of people laughing at the suggestion that there must be only one right scientific theory in each field, because it's the same reality we're talking about. That is my dream, a counter to the age-old dream of the single unified theory of the universe. And I hope by the end of this lecture I'll have got us just one step closer to it. Before giving a general philosophical argument for pluralism, I'd like to present one striking scientific episode for illustration. I said somewhere in my book, and I'll quote myself now, I became a pluralist about science because I could not honestly convince myself that the phlogiston theory was simply wrong, or even genuinely inferior to Lavoisier's oxygen-based chemical theory. It was a great formative experience to learn from my research on the history of the chemical revolution just how mistaken the common opinion about phlogiston was. Let me start by quoting from a popular source. It's always fun to beat up on something on the internet. So the website chemistryexplained.com tells you that Antoine Laurent Lavoisier is considered the father of modern chemistry. And by reading the chemical world of the phlogiston theory of combustion using quantitative analysis, Lavoisier was able to push chemistry toward its modern state. Generations of professional historians, Simon Schaffer included, have already done lots of painstaking work to explode this myth, but I want to push it further. For those of you not familiar with this history, I should explain what phlogiston is. And I think I'll turn down the lights a bit now. It all began with a wonder about how flame can emerge from a burning substance, apparently out of nowhere, like this. Where's the fire in that? So people postulated that fire must be present in a latent form in a combustible substance, and gave this fire the name of phlogiston. They saw combustion as the separation of phlogiston from the combustible, after which it assumed a very different form, like wood turning into ashes. Starting from this rather naive idea, the phlogiston theorists made considerable achievements. For example, they recognized that combustion, calcination, and respiration were essentially the same process. Dephlogistication, or oxidization in Lavoisier's later term. Calcination was the process in which a metal turned into a so-called calx, the earthy and crumbly stuff that we call rust or metal oxide. And it was in the chemistry of metals that the phlogiston theory had its most striking successes. Unlike normal combustion, calcination was easily reversed. So one could actually take a calx and reduce it back to its metallic state by adding phlogiston to it. You say, adding phlogiston? How do you do that? Well, for example, a crucial step in the smelting of metallic ores was the reduction of calx, which was achieved by mixing it up with a phlogiston-rich substance. So you take something combustible, like charcoal, and heating the mixture together. The resulting transfer of phlogiston from the charcoal to the calx turned the charcoal into ash and calx into metal. This was, of course, a very old process, which the phlogiston theory beautifully explained. And there are new experiments too. In 1766, Henry Cavendish reported that when metals dissolved in acids, they produced a combustible gas, which he called inflammable air. The acid must be attacking the metal and disengaging phlogiston from it, which explains why the resulting gas is combustible. Cavendish even thought that this gas was phlogiston itself. Joseph Priestley took this even further. He thought that he could make a dephlogisticated version of air by reducing a calx in air in an enclosed space. That's what he was trying to do when he ended up making what Lavoisier later called oxygen, as this blue plaque proudly proclaims. Priestley devised an even more striking experiment using Cavendish's inflammable air. If that gas was pure phlogiston, then it should combine with a calx, producing metal and nothing else. This prediction seemed a resounding success. When Priestley put a calx of lead into an inverted glass jar over water filled with inflammable air and heated it with sunlight focused by a large lens, the calx, as promised, turned into metal, and the volume of inflammable air decreased, shown by the water level going up. So Priestley said the calx was imbibing the phlogiston. Exactly as predicted. Now this is where things get really interesting. Lavoisier, initially very troubled by this experiment, came up with a brilliant reinterpretation. He said the calx is an oxide of the metal, and the inflammable air must combine with the oxygen in the calx and make water, which must have just fallen unnoticed into the pool of water underneath in Priestley's experiments. So he renamed inflammable air hydrogen, the water maker. Now, how did he get that idea? Well, because he had heard of another experiment made by Cavendish in the meantime, in which Cavendish made water by exploding a mixture of dephlogisticated air and inflammable air by passing an electric spark through the mixture. Doing Priestley's experiment over mercury instead of water showed that indeed there was water produced. So was that the end of the story? No. Because Cavendish immediately came up with his own reinterpretation, according to which inflammable air was not pure phlogiston, but water combined with excess amount of phlogiston. So when it gave up the extra phlogiston to the calx, it just became water, and the calx became metal. So you see that the phlogiston theory was not simply refuted by evidence. It gave intuitive and self-consistent accounts of chemical phenomena and even predicted some important new phenomena. Lavoisier's theory made sense too, of course, but it also had its own difficulties. For example, we should think twice before admiring his idea that combustion was combination with oxygen. How did he explain the light and heat coming out in the process? Lavoisier had to have recourse to a hypothetical substance of his own, which he called caloric, the fluid of heat, rejected by modern science as much as phlogiston is. Here you see Lavoisier's table of chemical elements, 1789, where we have light and caloric as the first two entries of chemical substances. All in all, in terms of empirical adequacy, simplicity, fruitfulness, or by any other standard criteria of judgment we use in philosophy of science, it is not clear that phlogiston chemistry was unequivocally inferior to Lavoisier's oxygen chemistry. The more seriously I delved into the details of this history, the less convinced I became. So I came to conclude that chemists in the late 18th century should not have abandoned phlogiston. I think science lost something when it killed phlogiston, and I'm in fact not entirely alone in that. William Odling, a leading theoretical chemist of Victorian Britain, thought that the phlogiston theorists were making advances towards energy-based chemical dynamics, which was stopped by the triumph of Lavoisier. Odling was sure that phlogiston really meant chemical potential energy. Even more striking are the musings of the 20th century American chemist G.N. Lewis, who did pioneering work on the role of electrons in chemical bonds and also gave us the famous definition of acidity, which is still current. Lewis said in 1926, it's the blue bit in the slide, "It is only in the last few years that we have realized that every process that we call reduction or oxidation is the gain or loss of an almost imponderable substance, which we do not call phlogiston, but electrons." The link between phlogiston and electricity was not a retrospective fabrication by Lewis and people like that. At least 23 authors from the 18th century are on record as having highlighted this connection. These included Priestley and also the apothecary John Eliot, who even proposed in 1780 that phlogiston should be renamed electron, as you can see on the fourth line from the bottom on that slide. That's just bizarre, but it's there. What if we had kept phlogiston? It is difficult to write counterfactual history of science, and I'm going to defer to Greg Radick, among others, to defend the cogency of that enterprise. But just imagine chemists and physicists working through the 19th century with the notion that metals were full of phlogiston, and phlogiston was somehow the same kind of thing as electricity. Would they not have tried to isolate this substance? They might have used ultraviolet light, for example. Why not? It was known by 1802, in which case they would have discovered the photoelectric effect. Or they might have tried to pass phlogiston between metal electrodes, evacuating the space between them in order to help its passage. Then they would have made cathode rays. It wouldn't have been left to J.J. Thomson 100 years later to discover the electron. In summary, I believe that the exclusive adoption of Lavoisierian system actually retarded the progress of chemistry in significant ways. Not only did it deprive people of the understanding of chemical processes that they had reached in terms of phlogiston, but it delegitimized some important scientific questions and closed off some fruitful avenues of investigation. I'm not saying that Lavoisier's chemistry by itself had these unfortunate effects, Rather, what was to blame was the dogmatic monist campaign that Lavoisier and his colleagues unleashed on science in an attempt to stifle any dissent from their new orthodoxy. Let me now turn to some general arguments for pluralism in science, having taken you through that particular case. The main point I'd like to make is that different benefits will spring from different systems of knowledge and from their interactions with each other. I say systems here rather than theories in order to emphasize that there's more to science than theories. So to begin with, there are what I call the benefits of toleration, which follow from simply allowing various systems to coexist with sufficient respect for each other so that each system can pursue its own potential. First, given the unpredictability of scientific development, we should keep multiple lines of inquiry open. Larry Laudan's pessimistic meta-induction from the history of science is a good reminder of the ultimate insecurity of our theoretical positions. Similarly, Thomas Kuhn emphasized the unpredictability in the historical development of science. There are some good cautionary tales here, such as Albert Michelson in 1894 and Lord Kelvin in 1900, declaring that physics was basically done, just on the eve of the great upheavals of relativity and quantum mechanics. The irony deepens if you realize that this Michelson was the same one in the Michelson-Morley experiment, which is said to have brought down classical physics. He never went with Einstein's theory himself, Michelson. Rational agents faced with unpredictability ought to hedge their bets, even if what they are looking for is the one ultimate truth. And if we respect other aims aside from ultimate monistic truth, there are additional arguments for pluralism. For example, if we want empirical adequacy for actual applications of theories, we should feel quite free to maintain multiple theories if they are good in different domains, even if they contradict each other in some deep sense. So for a long time in optics, for example, it made sense to keep both the wave theory and the particle theory, because they dealt effectively with different optical phenomena. Such division of epistemic or cognitive labor, as Philip Kitcher would put it, is more common than one might imagine. For example, can we do without classical mechanics? I don't think so, and if we can, I don't think we should be teaching that to every single student of physics. Imagine trying to give a purely quantum mechanical account of a spinning top or a rocket ship. As I learned from Nancy Cartwright and John Dupre, it is at best an article of faith that everything we need to do can be ultimately done with the latest and most fundamental theory alone. Even if we have different theories that are empirically equivalent to each other, it still makes sense to keep all of them, if we care about understanding. Gerald Horton emphasized the role of opposing sets of themata that underpin different types of explanation in science. Peter Lipton elaborated the notion of loveliness as the chief criterion of the goodness of explanation, leaving it somewhat uncertain as to whether loveliness was necessarily linked to likelihood. My own contention is that having multiple accounts of the same phenomena enriches our understanding. So give me the Heisenberg, Schrödinger, Dirac, Feynman, and Bohm formulations of quantum mechanics. All of them. Each provides a different kind of insight and an additional joy of understanding. This also reminds me of Pierre Duhem's infamous declaration that the ample and weak mind of the English physicist could only understand something by making a mechanical model of it, while the strong and narrow mind of the French physicist derived all the necessary understanding from formal mathematical systems, with no need for childish models. But if the English are the way they are, then they should be entitled to understand the universe in a way that is satisfying to them. And if we respect other aims, I've done that already. So far, I've discussed the benefits of plurality in satisfying a given aim of science, whatever that might be. Add to this the fact that people have different aims, and each of us may have multiple aims, then the case for pluralism becomes even stronger. There's no convincing reason to think that science has only one overriding aim or value. While Kuhn tried to privilege problem-solving ability as the key desideratum in science, he also gave us the list of quite a pluralistic list of accuracy, simplicity, consistency, fruitfulness, and scope as what scientists value in their theories. Bas van Fraassen gave us a whole list of pragmatic virtues, as he called them, including elegance and explanatory power. And I don't think Van Fraassen, gave a good argument for regarding these as secondary in importance to empirical adequacy. Once we grant that there are multiple human needs that science is called upon to satisfy, it is easy to recognize that we'll most likely not be able to come up with the perfect system that satisfies all of the needs. So much for the benefits of toleration. A whole other set of benefits arise from having multiple systems not only coexist, but interact with each other. In situations where none of the available systems by itself can achieve a certain aim well enough, we may attempt to do better by an ad hoc integration of different systems. There are examples from biology, but my favorite one is the global positioning system. GPS uses satellites that we keep in place by Newtonian physics and atomic clocks ruled by quantum mechanics and corrected by special and general relativity. With all of that, it maps the surface of the round Earth on a geostatic grid and gives advice to people on the ground from a flat Earth point of view. It all works beautifully. More generally, Peter Gallison argues, using C.S. Peirce's metaphor of a rope or a cable, that the strength of physics as a whole lies in its composition from independent yet interacting strands, which have different dynamics of development and non-simultaneous transition points. Even when different systems are not being pulled together to achieve a specific aim, one system of knowledge can benefit from the co-optation of empirical results, theoretical ideas, mathematical techniques, instruments, or materials borrowed from another system, even an apparently opposing one. So I mentioned how Lavoisier would not have arrived at his new chemistry without co-opting phlogistonist results, such as Priestley's production of oxygen and Cavendish's work on the composition of water. And even in the absence of integration or co-optation, different systems will interact if they are in competition. Philosophers of science typically mistake competition as the mere tallying of the accomplishments of each system achieved in total isolation. If you have an economist brother, you know this is not how competition works. Competition, in fact, sharpens the evaluation of each system, making it more difficult to be complacent about one's own assumptions or to leave weak arguments unexposed. And success in a neighboring system may induce one to pay attention to aims that one might otherwise neglect. Conversely, it is useful to keep even failing systems around as a reminder of valuable unachieved aims. Let me anticipate two major worries. I know you probably have lots more than two, but these are the ones that come up continually when I present pluralism. First of all, will pluralism not produce a relativist chaos in which the voice of reason is drowned out by a cacophony of quacks, charlatans, religious fundamentalists, New Age mystics, and plain idiots? Worse yet, without social authority vested in proper science, the relativist chaos may settle into the nightmare of one crazy faction taking over. recalled the horrors of so-called Aryan physics in Nazi Germany and Lysenkoism in the Soviet Union. But I say it's a grave mistake to equate pluralism and relativism. Relativism, as I understand it, at least in the form that horrifies people, involves an idle permissiveness and a renunciation of judgment. Pluralism doesn't renounce judgment, yet it maintains that it is better to foster a multitude of worthwhile systems rather than only one. So my slogan for pluralism is not anything goes, but many things go. Pluralism also takes a stance against absolutism. A system of knowledge that denies the rights of other systems to exist would have to be banned in a pluralist regime, just as a truly free society has to ban political parties that exercise an unhealthy dominance over other ones. But you say, that's all fine. Can we afford it all? Don't we need to pool our precious resources into one line of inquiry in each field? I have three layers of responses to this worry. First, in the modern era, science is not so under-resourced. Surely there are enough resources to go beyond the strict monopoly. Just how pluralistic we can go is the pertinent question. Secondly, there are points of diminishing return. I think modern science has actually tended to put too much investment into monopolistic lines of thinking. Having too many people trying the same fashionable approach can be wasteful. What has been the return, for example, from investing so much of the best talent in theoretical physics in string theory? Finally, it's a pessimistic fallacy to assume that the amount of resources that society devotes to science will remain exactly the same. Pluralism itself may even inspire more people to do or support science. Now, even if you are persuaded that science would benefit from more pluralism, you may still be skeptical that HPS can do anything about it, beyond pointing out that pluralism is a good thing. For example, when I talk about what phlogiston could have done if it had survived, you may think, that's all very interesting historically, but what relevance does it have now? Haven't we by now learned all the lessons that phlogiston could have taught us? What can a look back at the distant past of science really teach us? To these questions, now let me present two other cases, which I hope will persuade even the skeptics. The first one briefly. The promise of learning new science from the past first hit me when I was doing research on the history and philosophy of temperature, which was the subject of my first book, which the Vice-Chancellor kindly mentioned. This book begins with a philosophical question about how the so-called fixed points of thermometers could have been demonstrated to be fixed in the absence of previously agreed fixed points, which could serve as criteria of judgment. Once I asked that question, I easily discovered that there once was a significant scientific debate about this. The urgency of the problem was such that in 1776, the Royal Society of London appointed a special committee to address this problem, chaired by the illustrious Cavendish. Among the members of this committee was a man called Jean-André de Luc, a native of Geneva who later settled in England as tutor to Queen Charlotte. A meticulous meteorologist, de Luc made his initial fame by using improved barometers to measure the heights of mountains. I was intrigued to learn in his 1772 text of meteorology that water did not always boil at the so-called boiling point, even when it was pure and even when it was under standard pressure. By the mid-19th century, there was a well-established and sophisticated body of knowledge about the intricacies of boiling, which has been forgotten by 20th century physicists. I was able to reproduce many of these old observations through my own experiments, kindly hosted by Andrea Sella and other colleagues in the chemistry department at UCL. They were kind to suspend their judgment on the question of my insanity, and they asked me, "What do you need?" I said, "Well, some water." But it has to be distilled water, so they gave me an indefinite supply of that. Let me give you just one example from Deluc's work. He was unhappy about the standard setup of boiling point experiments as shown there, in which one measures the temperature of the main body of boiling water, while the vapor bubbles were only produced in the first layer of water in contact with the heat source. Barking up the wrong tree. We want to know what the temperature is where the bubbles are produced, not somewhere else. So, what you see here in this video I'm going to show you is my approximation of Deluc's attempt to bring the whole body of water to the same temperature as that of the first layer by heating water slowly while minimizing the loss of heat at the surface. So here we have distilled water in a flask with a long thin neck being heated on a hot plate, which is much gentler than the usual naked flame. Right? As the temperature approaches 100 degrees, the water starts boiling, in quite a normal way, as you see there. As boiling continues, however, the temperature continues to rise, while the bubbles get bigger but less frequent. They also come more irregularly, often in bursts. The temperature goes over 100 degrees, easily reaching 101 or 102, while the boiling is reasonably steady. This is what 19th century observers termed bumping. Later in the process, we can see what Deluc called puffing. With continued heating, the bubbles can become even less frequent, while temperature creeps up further. Often there are long, quiet periods punctuated by very large bubbles. Sometimes the puffs are explosive, throwing some water out of the flask. It's about to do that. The trial shown in here, in this clip, produced a temperature of 104 degrees during puffing, as you see on that thermometer on the side. The behavior of the water in this setup is completely different from what we usually see when we boil water. But they are entirely consistent with what Deluc reported in 1772. There's much more to show and tell you, but I must move on. Some of you know that I will talk about boiling for hours and hours, if you let me. I'll only mention generally that it was widely known in the 19th century that the temperature and behavior of boiling water depended greatly on the material of the container, the amount of air dissolved in the water, and the exact manner of heating, and so on. Nowadays, only engineers who work on heat transfer seem to know something about all this, and even they don't discuss everything that Deluc knew in 1772. There are vast numbers of scientifically educated people today who unsuspectingly recite from their textbooks that pure water always boils at 100 degrees under standard atmospheric pressure, scolding children and marking down students if they fail to repeat this particular piece of untruth. Even better examples of recovery from history come from my current work on early electrochemistry, starting with Alessandro Volta's invention of the battery in 1800. For hosting this ongoing work, I thank Darren Caruana at UCL and Peter Waters here in Cambridge and their colleagues, and also the Leverhulme Trust for financial support. You'll see in a moment why money was needed. It's also a pleasure to acknowledge my fellow travelers in historical experimentation, especially Rosie Coates, Georgette Taylor, and Jenny Rampling. Now, if you saw the poster for this lecture, you will have wondered what on earth this is. It's a silver tree grown to an early 19th century recipe. Actually, it's not much of a recipe. You just stick a copper wire into a solution of silver nitrate. That's it. Maybe you've seen something like this, but usually it's done with a battery. My experiment, which I learned from Michael Donovan of Dublin, you've never heard of him, that's part of the point, drives itself. This is from Donovan's textbook of galvanism in 1816. Now, this is all it takes. A piece of copper wire and a flat plastic envelope filled with a silver nitrate solution. About 1 molar concentration works pretty well. And the dark green piece of paper is just there to provide a visual backdrop. Now, when you insert the copper into the solution, it gets immediately covered in a deposit of silver, as you see there. Now, this kind of replacement reaction was known for centuries. In the 18th century, it was typically said that the nitrate had a stronger affinity for copper than for silver, so that copper went into the solution in exchange for an equivalent amount of silver coming out. But if you keep watching, more silver starts growing on the silver. These are the formations I got in one experiment after 9 minutes, after 26 minutes, and 88 minutes. Isn't that one beautiful? And this is one I grew in a cup rather than in a flat envelope. Let me show you another simple, extremely simple experiment that is unfamiliar to most scientists today, and this one's actually related to the silver tree. This was done in 1801 by William Hyde Wollaston, who was the masterful processor of platinum, made enough money out of that so he could quit his medical practice and just do chemistry. And he was also co-discoverer of ultraviolet radiation. Wollaston began with Cavendish's observation that certain metals dissolved in acids, releasing bubbles of hydrogen. So for instance, in the clip you see here, so here we are. So what you see here is a zinc wire dissolving in hydrochloric acid, producing hydrogen gas. Add to it a copper wire, and no reaction happens there since hydrochloric acid is powerless to attack copper. But if you just make the two wires touch, hydrogen bubbles immediately start issuing from the copper as well as the zinc. The copper is still not dissolving, it's just producing bubbles on the surface. Now, why did it occur to Wollaston to do this experiment? I mean, one answer is why not? You'd almost do this by accident. But he was trying to understand how Volta's battery worked. So each unit cell in Volta's battery consists of two metals with an electrolyte layer between them. The simplicity of Volta's invention was really one of the most striking things about it. You can also do this. So I've got a little prop here. That's exactly what you see in that picture. And what you can do is make this V shape with copper and zinc wire twisted to each other, and you touch your tongue with it. Yeah. On the zinc side, you'll feel this very strange acidic taste. And you disconnect the wires and you don't have that taste anymore. So I've just made a battery with my tongue, which is also registering the flow of electricity. Now you can try that at home. Just make sure the wires are clean and not too sharp at the end. These experiments are so simple to make, but surprisingly difficult to understand. Wollaston thought that in his experiment, the acid attacked zinc and released the electric fluid from it, which was then conducted over to the copper wire. Why it went to that side, he didn't say. Modern textbooks say something like this, that hydrogen ions, H plus in the picture, which are plentiful in the acid, take electrons from the metal, turning themselves into hydrogen gas. And this transfer of electrons also ionizes the metal, which dissolves in the acid. But if that's what happens, how does the reaction generate any excess electrons that travel over to the copper side to make hydrogen gas there? which is what you see in Wollaston's experiment. Volta's own view of these things was very different. Volta thought that it was the contact between the two different metals, not chemical reactions, that generated the flow of electricity in his battery. For him, the wet stuff was just there for non-metallic conduction of electricity. So there was a long and complex debate on this issue, which didn't reach a clean resolution even into the 20th century, by which time the debate fizzled out because it wasn't important anymore. I mean, who cares how the battery works if you're doing quantum mechanics? But you may say, surely modern chemistry has a firm understanding of how the voltaic battery works. I'm not so sure. In fact, I'm so unsure about this, I'm going to write a whole book about it. Everywhere I look in introductory modern textbooks, what I find is this, an account of the Daniell cell, in which the electrolyte consists of two different solutions connected by a salt bridge or through a porous barrier. In this setup, each metal is dipped in its own solution, and the electrical action is easily explained in terms of the imbalance of the redox potentials of the two sides. Volta's original cell cannot be explained this way. Advanced textbooks will tell you to write down and solve the Nernst equation for the system of interest. But I've not seen that done for Volta's arrangement. And also, generally, the thermodynamic treatment ignores the contact potential entirely. The puzzle deepens when we remember that Volta himself was not even using acids but salt water. This too is easily reproduced. So there's my rendition of the voltaic arrangement, showing a very healthy voltage and even a non-negligible current. And it can be understood what's going on here if we suppose that the negative ions, in this case the chloride, attack the zinc to remove the positive metallic zinc ions and set some electrons free. But then what happens to these electrons when they get conducted over to the copper end and enter the solution? There aren't very many hydrogen ions in salt water to receive these electrons, which explains why no hydrogen bubbles are seen in this experiment. There are plenty of sodium ions, but if they received the electrons, we would have elemental sodium being produced in water, which would have explosive consequences, which we don't. So where can the electrons be going if there aren't enough positive ions to receive them? In my theoretical desperation, I thought maybe they were just being conducted through the salt water without making chemical reactions. If so, I made a prediction. Current should still pass if I divide up the solution into two parts and connect them with a chemically inert conductor, such as a gold wire. So I set up that experiment, and because I expected it to go very slowly, I helped it along by driving it harder with a couple of external commercial batteries. And this is what I got within a few hours. That weird stuff in the left-hand tube, which is grown on the copper wire, that could only have come from the gold wire somehow. But how? This set me off on a new line of work to investigate what happens to gold that's used as the anode, the positive electrode, in the electrolysis of salt water. To minimize distractions for the cathode, I used a graphite rod, so cathode on the negative side. Graphite's really quite inert chemically, so it makes things simpler. So that's the setup, and a little close-up of it. Now I was using a variable DC power supply instead of batteries, so that I could monitor what happens as the external voltage is gradually increased. As you see, nothing at all happens up to about 2 volts, but when it gets to 2.2, there's a slight bubbling that you see on the graphite, again on the cathode, and that's a close-up of that. That's hydrogen bubbles beginning to be made. By the time the voltage is about 3 volts, the bubbling is quite vigorous. And what is it that's going on the gold side? Let's see what's going on. the gold is dissolving in a clear yellow streak, while hydrogen gas is produced on the negative electrode. And you can see the solution of gold. I think it must be some kind of chloride. I need to go and analyze that in a serious way. The yellow stuff is collecting at the bottom. And this reaction can be quite impressive at its height. This is at a slightly higher voltage. Is that showing okay? Yes. So it keeps going like that. And the interesting thing about this is this happens only in a very, very narrow window of voltages, between about 2 and 4 volts. So when the voltage gets too high, the dissolving of gold stops. Instead, you start getting bubbles from the gold. Can you see the bubbles there? Yeah. And the graphite is now beginning to physically disintegrate, so you see the black specks. And there must be chlorine gas being produced here, judging from the smell that I get at that point. And don't worry, I didn't stay too long with that. Some of you know how fond I am of chlorine. Anyway, and it continues on at higher voltages like that. I have not yet met anybody who had seen this before or has not found it surprising, including dozens of professional chemists that I've shown it to in several countries. And it vindicated the healthy skepticism and good sense of my wife, because when I asked her if I could use my wedding ring for a previous experiment requiring a piece of gold, she said no, despite my assurance that nothing will happen to the gold, I promise you. All very curious, but so what? If I may say so myself, in the last 20 minutes or so, you have witnessed something extraordinary. A genuine recovery of lost scientific phenomena from history. A set of intriguing theoretical questions surrounding those phenomena. An extension of the recovered knowledge through theoretical reasoning and new experiments. And an enhancement of critical awareness about the limits of currently accepted ideas. And to me, the most amazing thing about this is the ease with which all this is achieved, once you get a sense of where to look and what to push. Let me finish by returning to my original question. Why should this great university and other universities in the world and society at large, the proverbial taxpayer, support something as strange and esoteric as HPS, especially if we're only going to destroy gold rather than making it? In the light of the concrete material I have now presented, I think my abstract answer will make more sense to you. HPS is the best vehicle for pluralism concerning science, and pluralism will make science richer, more flexible, and more progressive. I think HPS is at its best when it deals with the weird and wonderful in science, and when it poses awkward questions regarding the content, aims, and methods of science. It is uniquely valuable when it deals with science that is unknown to scientists. If HPS only delved into what fits nicely into current science and its self-image, there would be no need to have a separate academic discipline for it. In pluralist HPS, we have a very tricky balance to strike, to look at the content of science from an independent angle while not looking away from it. The training of specialist scientists produces a tendency towards consensus on the basics. Philosophers, on the contrary, are free to ask questions without restrictions, to expose and challenge unjustified assumptions, and to consider unorthodox alternatives. The spirit of pluralism strives towards a maximal state of knowledge, in which nature is seen and enjoyed in all its abundance. To reach this ideal, we need all the available sources of help, including the past. With proper respect for the past masters who did their best to understand nature, we can wade into history, picking through what today's scientists may consider junk. Not everything that scientists have thrown out is worthless. Specialist historians of science can make independent critical judgments as to what from the past is worth preserving in active memory or even bringing back. Let me have more light as I anticipate some final worries. A worried question I anticipate from the historians, who say, shouldn't the understanding of the past be appreciated for its own sake? I can hear Kuhn's formidable voice saying he just wants to climb into Copernicus's head to see what it was like, and that it is irrelevant for the historian whether this helps scientific knowledge now. But that cannot be the whole story. It's difficult to imagine why we would expend blood and sweat minutely dissecting and reconstructing musty old systems of knowledge if we didn't see some insight or beauty in those systems, whether they be medieval alchemy, magic, and medicine, or early ideas of evolution and reproduction, or early modern pneumatics, optics, and astronomy, or ancient Babylonian mathematics, or the construction of astrolabes and orreries, or pre-DNA genetics and horticulture, or Freudian psychoanalysis, or the origins of modern economics. That's just a 20-second glance at the range of work going on in our department. From the philosophers comes a different worry. Shouldn't philosophy concern itself with general principles of knowledge rather than getting mixed up in specific details of science? I couldn't disagree more. General and abstract principles certainly fall into the domain of philosophy, but only where science neglects them. It's useful to think back to the time when all scholarly endeavor was considered philosophy. Starting from that, after every successful specialism carved itself out, what we now call philosophy is the leftovers, just the inconvenient questions, really. It is an unhelpful conceit to think that we philosophers only deal with the lofty, universal questions. There are also specifics that we ought to worry about, because no one else does. To serve the pluralist function properly, the philosopher of science needs to delve seriously into the details of the science under examination, whether it be natural selection, clinical trials, economic modeling, quantum field theory, space-time physics. Again, just to mention some local work very briefly. It makes little scientific impact, for example, to talk about the underdetermination of theory by evidence if we don't study actual alternatives. HPS seriously undersells itself if it does not claim its knowledge-generating function in relation to science. When we dig up strange past systems of knowledge and make sense of them, or when we recover forgotten experimental results, we are enriching the stock of human scientific knowledge. Even mere critical awareness enhances the quality of knowledge, because we do not truly know anything unless we know how we know it. And if critique should actually lead to alternatives, even better. Pluralism gives us this broad view of what constitutes scientific knowledge and shows us how HPS can contribute to it. In this enterprise of pluralist knowledge building, the philosophy of science and the history of science work best hand in hand. The topics and problems dealt with by history of science and philosophy of science are connected through their shared exclusion from current specialist science. And there are dynamic and productive interactions between philosophy and history. For example, learning about the astonishingly varied and unexpected conceptions and practices of past science can sharpen the critical awareness of philosophers very effectively. I say historical truth is often stranger than philosophical fiction. On the other hand, philosophical questioning can generate lines of historical inquiry that unphilosophical historians overlook. Both of my own books came to be written that way. So we should say HPS not only for brevity and convenience, but to emphasize the essential connection between the H and the P. Let me conclude now. Taking a pluralist viewpoint allows us to recognize that any specialist system of science only deals with a restricted range of things in a restricted range of ways. No system of knowledge in science should be given the right to suppress, exclude, or delegitimize all others. We need as many of the best systems as we can afford to maintain in order to give ourselves maximal exposure to reality. Gaining knowledge in such a maximal way also contributes to the full actualization of human potentials. After many centuries of struggle, we have learned to accept and benefit from a spirit of pluralism in the realms of politics, culture, language, cuisine, art, and ecology. I believe it is time to admit it in science too. Pluralism will not only enrich scientific knowledge itself, but also contribute to the maturing of the role of science in society. By helping science move beyond the arrogance of youth and enter into an open-minded and constructive engagement with other spheres of life. Pluralist HPS could trigger a decisive transformation in the nature of our science. Alongside the expanding store of current specialist knowledge, we can cultivate a complementary body of knowledge that combines recovery, extension, and critical awareness. Such complementary scientific work would by its nature be more accessible to the non-specialist than science normally is, even at its elementary levels. A full integration of pluralist HPS into science education and into public intellectual life would be a momentous step, enabling the educated public to participate once again in the cultivation of our knowledge of nature. Thank you very much.